Resonance is a fundamental physical phenomenon where a system oscillates at significantly higher amplitudes when it is driven by an external force at its specific natural or resonant frequencies. In music, instruments act as resonators. They function by selecting specific harmonic frequencies from a complex sound source and amplifying them. The physical geometry of an instrument determines which waves survive. By organizing chaotic air oscillations into standing waves, the instrument transforms energy into structured musical tone. Standing waves occur when waves reflect off boundaries, interfering with themselves. In a string fixed at both ends, only specific frequencies persist. Points of no movement are called nodes, found at the boundaries. Points of maximum displacement are antinodes. The instrument's length dictates these positions. As we increase frequency, we form higher harmonics with additional nodes between the boundaries. This geometry is what defines the pitch. Traditional wave theory is linear, modeling instruments as ideal, static resonators. However, real instruments are nonlinear systems. In reality, structural movement of the instrument body creates a feedback loop with the air column, resulting in complex, living waveforms. We must treat instruments as dynamic systems where structural deformation influences the air and the air column influences the structure. This constant interplay creates living waveforms that evolve in real time, moving far beyond the limitations of simple linear physics. Animated dynamics reveals that musical instruments act as living, breathing systems. As a musician plays, the structural components of the instrument are in constant motion. The wood plates of a violin, for example, undergo microscopic deformation, effectively oscillating with every note. These vibrations are not passive. They interact dynamically with the air columns inside the cavity. This interaction creates complex feedback loops, generating the rich, unique timbre that defines a master-crafted instrument. By viewing these movements as an animated, nonlinear dynamic system, we gain a deeper scientific understanding of why specific wood grains and shapes produce superior musical voices. AI-driven fluid structure interaction has revolutionized acoustic science. By combining computational fluid dynamics, or CFD, with finite element analysis, or FEA, researchers can finally map the complex relationship between air and matter. CFD models the fluid air, while FEA tracks how the instrument's structure flexes under pressure. AI bridges these simulations, allowing us to visualize the hidden, tiny vortices that actually define the texture and color of a musical note. This unprecedented clarity enables engineers to predict sound characteristics before a single piece of wood is shaped, marking a new era of digital acoustic precision. Computational fluid dynamics allows us to observe the hidden behavior of air inside an instrument. Air enters as a laminar flow, but the internal geometry forces a dramatic transformation. The interaction with edges generates complex vortices. This is a fluidic pulse, not just a simple wave. By visualizing these vortices, we understand how instruments shape air into sound. Modern acoustic research has moved beyond static mathematical models. We now utilize real-time multi-physics simulations. These models capture how thermal, mechanical, and acoustic forces interact instantaneously. By integrating these forces, researchers can observe how energy transforms into sound during a live performance, providing a comprehensive understanding of acoustic dynamics. Active metamaterials are revolutionizing instrument design. By embedding piezoelectric actuators directly into the structural components of an instrument, we can create a bridge between digital control and physical acoustics. Piezoelectric actuators act as smart control points. When a voltage is applied, these materials undergo mechanical strain, effectively altering the mechanical impedance of the instrument's body. This dynamic control allows the instrument to change its resonant frequency mid-note. We can shift from a standard wave profile to one that mimics the specific harmonics of historical instruments. By manipulating these internal structures, a single device can replicate the unique acoustic footprint of instruments across different centuries, turning passive wood into a programmable sonic entity. Using laser Doppler Vibrometry, or LDV, scientists can now map the surface of musical instruments in 4 dimensions. 3 spatial coordinates plus time. This technique reveals that no part of an instrument is static. Even components we perceive as rigid vibrate dynamically while being played. These invisible oscillations define the instrument's acoustic signature, transforming a static object into a complex, resonating system. Damping is not merely the silencing of sound, it is a precise energy filter. By controlling the dissipation rate of energy within the wood, designers regulate the attack transient. The attack transient represents the initial burst of sound energy. High damping quickly absorbs the sharpest peaks, creating a warmer, less brittle personality in the final tone. Brass instruments often suffer from intonation drift as the internal air temperature rises from the player's breath. This causes the metal to expand and the pitch to shift. Modern breakthroughs utilize 3D printed bores embedded with shape memory alloys. These materials react to thermal changes in real time. As the temperature increases, the alloy automatically alters the internal diameter of the bore, compensating for the thermal expansion of the air column. This dynamic correction ensures the instrument remains in tune, regardless of how long or intensely it is played, maintaining orchestral intonation. Brass instruments often suffer from pitch drift due to thermal expansion. As the air inside warms, the effective acoustic length changes, shifting the resonant nodes. Dynamic bore technology automates the adjustment of the internal tube diameter. By utilizing shape memory alloys, the instrument compensates for heat in real time. This mechanism ensures that the resonant frequency remains constant, providing stable intonation regardless of how long the instrument is played. Luthiers now create digital twins of instruments. These are complex mathematical models that simulate an instrument's physical properties before a single piece of wood is cut. Before manufacturing, the entire resonant structure is analyzed. This simulation predicts how specific woods and thicknesses will vibrate under tension. Designers can optimize internal structural ribs and material thickness. By adjusting these parameters digitally, they ensure perfect acoustics. This technology minimizes material waste and guarantees professional-grade resonance before the physical instrument is even built. Digital twin technology allows manufacturers to perform virtual stress tests on instrument structures. By adjusting internal rib placement, they can precisely tune the soundboard's mechanical response. By modifying the stiffness of these ribs, engineers observe how resonant frequencies shift, creating a more predictable and superior acoustic profile. Neuroacoustic coupling is an emerging scientific field that explores how the physical resonance of a musical instrument directly interacts with the human vestibular system. By targeting specific sympathetic frequencies, researchers can design instruments to create a more intense perceived resonance for both the performer and the audience. The internal ear translates these structural vibrations into neurological signals. Designing for these frequencies maximizes the emotional and sensory impact of the performance. Neuroacoustic design shifts our focus from purely mechanical sound production to the human experience of that sound. The goal is to harmonize an instrument's mechanical output with our unique biological response. This approach involves tuning an instrument specifically for the human ear and body. It targets not only the hearing pathway, but also the vestibular system, which processes motion and equilibrium. By mapping the frequency spectrum against neural activation patterns, engineers can optimize instruments. This ensures that the acoustic resonance aligns with the listener's sensory system, maximizing perceived quality. Ultimately, neuroacoustic design treats the instrument and the human listener as a single, coupled feedback system, elevating the performance into a holistic biological event. As traditional tone woods become increasingly rare, the instrument industry is turning to sustainable innovation. Researchers are developing bio-based resins reinforced with carbon fiber. These acoustic composites are engineered to replicate the complex cellular resonance of spruce and maple. By matching these structural patterns, we can achieve high-fidelity sound quality, ensuring musical excellence without ecological damage. AI-assisted acoustic optimization is revolutionizing how we manufacture instruments. By applying precision stress to materials during production, we can simulate decades of natural aging. This technique effectively cuts the break-in period of professional concert instruments by up to 40%. The AI pre-stresses the structure, reaching the optimal resonance state without the weight. We are shifting our paradigm to view musical instruments not as passive objects, but as biological mechanical hybrids. During a performance, the player, the instrument, and the air function as one. The player's body energy, the structural resonance of the wood or metal, and the fluid air column are not separate entities. They form one inseparable wave equation. The vibration is a continuous feedback loop that defines the sound's character, blending physics and biology into a single resonant phenomenon. Our journey through the physics of sound has brought us to a profound conclusion. We have evolved from viewing instruments as simple linear resonators to understanding them as complex, animated, and living dynamic systems. By mastering resonance through fluid structure interaction and smart materials, we are redefining what it means for an instrument to sing. Today's instruments are biological mechanical hybrids. The interaction between the player's body and the instrument's structure is now inseparable from the wave equation. The future of music lies in this mastery of animated dynamics, where every nuance is calculated, simulated, and perfected.